So I promised you last day that it's going to get weirder. Already last day it got pretty weird. I'm just going to do a quick review. You do not need to know this for the test. This was to give you the setup. I told you Einstein came along and he said, I'm going to start with two postulates, two theories. First thing he said is, I'm going to assume physics doesn't change anywhere in the universe. But he also said, I notice things behave differently when we're accelerating, and I don't know how to explain that yet. So he said, as long as objects are going at constant speeds relative to each other, the laws of the universe will be the same. But he said, like, I notice when I go around a corner, something dangling from my mirror in my car suddenly starts pointing sideways. I can't explain that yet. I'm not going to deal with that yet. Or you can feel acceleration. You all know, have picked up on that, yeah? You can feel when you're going around a corner. But if you're at a constant speed, you can't feel it. You may even have noticed if you're in a really good elevator that's really well designed, because there's no windows, because there's no doors, you actually can't tell that you're moving, except you look at the floors and you know the numbers are moving. So intellectually you know you're moving, but you can't feel it. Einstein said, yeah, there is no way to detect constant velocity. You could be moving, you won't know it. The laws of the universe will be the same. And then he said, all right, I'm also going to agree with the results of the Michelson-Morley experiment, that no matter how you are moving relative to a beam of light, whether you're moving towards that light, which if it was a baseball would mean you would add the speeds together, whether you're moving away from the beam of light, which if it was a baseball means you would subtract the speeds. That light doesn't work that way. You're always going to get the same answer. And that means since speed is distance over time, we got weird stuff happening with distance and time, if we're always getting the same answer for speed, regardless of how we're moving. Then he brought in his lovely thought experiment of the glass spaceship, and he very cleverly said, if I can write distance three different ways, if I can write this vertical line distance here as the speed of light times time on the spaceship, that's distance because it's speed times time. If I can write the distance the ship travels forwards as its speed times time, that time is what we measure back on Earth or for the stationary observer. And this is where we said if you throw a baseball from outside, it looks like a diagonal path. The beam of light as seen by the stationary observer, which would be the speed, which is going to be the same no matter what, times the time for the stationary observer. Got to give him full credit, Daniela. Pythagoras, Math 8, Math 9, a little factoring, and out he came with his time-dilation equation. And we noticed things like, holy smokes, that means it's possible for an astronaut to return home and be 11 years younger than his daughter. Whoa. It gets stranger. So you ready? Where we left off. You want your green sheet out? Because later on today, we're going to do one more equation derivation, but it's such a pain. This is going to be the only time when I say it's not worth doing it in your head. We're going to write the new equation down. If you're wondering, we're going to get the letter v by itself inside that time equation. And that letter v is inside a squared, inside a square root, on the bottom of a fraction. We'll do that once and then not do it again. But not only does time behave strangely, space-time behaves strangely. Proxima Centauri is the closest star to the Earth. It's 4.2 light years away. My abbreviation for a light year is going to be an L and a Y. I'll never write my lowercase l like that, because what does that number does a lowercase l look like? So just so you don't mix it up, you'll see. Notice I always cursively write my lowercase l. There may be a proper abbreviation for light year. I don't know what it is. It may be L period A, because technically the abbreviation for years is A. But anyways, Proxima Centauri is 4.24 light years away. That means it takes light 4.24 years to get to us. What is a light year? A lot of people think it's a measure of time because it has the word year in it. Is it a measure of time? Yeah. It's not. You could actually read the next line down where it says note and just read it yourself, but yeah. It's a distance. It's a distance. We're going to make a little note here. Can you do me a favor? Next to this question, can you write d equals v times t? Again, Jenna, really it's d equals VIT plus a half AT squared, but I told you Einstein said, I don't know how to deal with acceleration at this level yet, so we're not going to accelerate, which means it's going to be d equals VIT, but since VI is VF is V, if you're not accelerating, I'm going to even drop the I. Okay. How big is a light year then? A light year is the distance light travels in 1 year, which is going to be v times t. How fast does light travel? I mentioned this in lesson 1. Taylor, you're right. 3 times 10 to the 8th meters per second. I've realized I forgot to put this on your green sheet. So one thing we're going to do on the back page at the bottom where you have all the relativity stuff, you can make a, what's the symbol we use for the speed of light? Do you see? You can go c equals 3 times 10 to the 8th meters per second. Some kids memorize it because it's fairly easy. It's a 3, but just in case, realized I forgot to put that on there. So the speed of light that I would put in for v here then would be 3 times 10 to the 8th. What's the time in a light year? So it's going to be 365 times 24 days times 60 times 60. The reason we have to do that is the speed is in meters per second, so we are going to have to convert our time to seconds. Just purely for nerdishness, how big is that? Get your calculators out, let's find out. This also is, because you're going to need to know where your scientific notation button is again. So this is a bit of review, because later on today we'll be using the scientific notation. My scientific notation button is that little EE thing, wherever yours is. And that's going to be times 365, times 24, times 60, times 60. As a nerd, I've memorized it's really close to 2.5, yeah? When you hit equals? Isn't it? Oh, sorry, 9.5. 9.5. I haven't memorized it right. That's in meters. If I divide by 1,000, this gives it in kilometers. It's 9.5 times 10 to the 12th kilometers. That's a light year. Don't write this next bit down, but just to give you how big the number is, that means it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A light year is 1,000, million, billion. What comes after billion? Trillion. It's almost 10 trillion kilometers. Not quite. 9.5 trillion kilometers. I can't quite wrap my brain around that. Although, remember at the beginning of the year, I showed you that web page that had big numbers in terms of pennies? I think a trillion pennies was the cube that covered the entire football field and had a little tiny little person standing next to it. That was a trillion. So 10 of the whatever. To try and give you a little more distance perspective, that's how far light travels in 1 year. How long does it take light from the sun to get to the earth, roughly? Anybody know? About 8 minutes. So that's a big distance. That's 8 light minutes. Light years bigger. That's not on your test, but since we're going cosmic, I always like to try and give you an idea of what's big and what's small. All right, now let's actually jump into the question. It says, suppose we build a spaceship that can travel at 80% of the speed of light, 0.8 c. How long will the spaceship take to get there as measured by the stationary observers on the Earth? What's this question asking me to find? Someone said TO, the receiver that was a loudmouth. Someone said time. Lyndon, what? Okay, this is asking me to find T, and I'm going to be really fussy. Can all of you right now underline the phrase, the stationary observers on the Earth? We're not moving on the Earth, which means we don't need to use Einstein's equations for this calculation. We can use Physics 11. We can use D equals VT. We can get the T by itself. How? Hello? How? Divide the V. Okay, so the time, as far as we're concerned, it takes light this long to get to us. It's going to be D divided by V. It's going to be 4.24 light years divided by 0.8 C. As far as we're concerned, I think I said how long it takes the light to get to us. I misspoke. This is how long it would take the spaceship, as far as we're concerned, to get to there. Don't go to your calculator just yet, Taylor. One more thing. You can sort of imagine that this light and this speed of light cancel. They do in that you will get an answer in years. How many years do we think the trip will take? Now you can go to your calculator, Taylor. How many years do we think the trip will take? Well, it's going to be 4.24 divided by 0.8. And I get 5.3 years? Yes? So there and back, we would say 10.6 years. Not too bad. How long will it take to get there as measured by the observers on the spaceship? What's this question asking me to find? T0 on the space on board was the dumb way I had you remember that. Okay, so I'm going to make a little note here. T0 equals question mark. I guess that means they told me time back on Earth. What? 5.3. That's why we had to do part A first. Okay. And how fast is the spaceship moving? Oh, 0.8 C. See on your green sheet the time dilation equation? Now on your green sheet the T is by itself. What do we want by itself? How would I do that? What will I do with that square root thing? How will I move it to the other side? Times it because it's divided. Okay, so T0 equals T times the square root of 1 minus V over C all squared, which is going to be 5.3, 5.3 square root of 1 minus 0.8 C over C squared. Do you see? Do you see? See? Do you see? So 5.3 years for us, 10.6 years there and back. How many years on the spaceship? Okay, I'm going to go. By the way, like I think on your calculator, you can do this in one fell swoop quite nicely. Go ahead. That's great. I still have to go 1 minus 0.8 squared, square root button answer, and then multiply that by 5.3. And I get 3.18 years? Yes? I said years up here. I keep using a Y. I'm trying to break that habit. The proper abbreviation for years is A for annually, not yards. Anyways, I won't take marks off if you put a Y there. I'll figure it out. So the trip there and back on the spaceship would take 6.36 years. Okay. What's the distance traveled according to the observers on the spaceship? Now, on the Earth, we're saying that the distance is 4.24 light years. What about on the spaceship? What speed is the spaceship traveling? How much time elapses on the spaceship? Look up. I'm going to get an answer in light years, C times A. So just go 0.8 times 3.18. You don't realize how weird that is. That means if somehow the spaceship stretched a tape measure as they were going along, their tape measure would measure 2.54 light years long, even though our tape measure measures 4.24 light years long. Well, no, it's weird, yes, but wait a minute. I told you, look, if we always get the same speed answer, but speed is distance over time, not only should weird stuff be happening with time, weird stuff should be happening with distance too. There is no right distance. There is no correct distance. It's impossible to say how far apart any objects in space are. It all depends how fast you're moving. You'll get if you're moving faster and a different speed than me, you'll get a totally different answer for when you're measuring how far apart planets and galaxies and stars are than I will. Why? Because space-time is what's changing. And that's why Einstein called it space-time. He said, I'm not going to even distinguish between the two, space, distance, and time. I'll call them one thing, because something weird's going on with both of them. Oh, it gets weirder. Turn the page. Yet cooler. Let's suppose you could travel at the speed of light. How much time would elapse if you're traveling that fast? So if our spaceship is traveling at the speed of light, we would like to find T0, the time on board the spaceship. What was the equation that had the T0 by itself? T0 equals T times that square root thingy. By the way, next class we're going to give that square root thingy a special name. It's called the gamma function. Anyways, you okay with that so far? Equals, I'm going to leave the T there because I'm not quite sure what to do yet, but 1 minus over C. How fast is our spaceship traveling? What's our V if we're traveling at the speed of light? It's so obvious that it's tricky. More specific, I have a symbol for it, don't I? Okay, let's make a little note in our data up here. We're really asking what happens if your spaceship is going C. Exactly C, not a percentage, exactly C. So I'm going to put a C there, squared. Do you see? Do you see? Do you see? What do you get inside the bracket when you go C divided by C? 1 squared. So you get this. What, Luke? Or was it Taylor? What, Taylor? In your head, what's 1 minus 1? 0. What's the square root of 0? 0 times T. What's anything times 0? If you're traveling at the speed of light, there is no time. So, you ready? I just told you that it took sunlight 8 minutes to reach the Earth. That's only relative to us. If you were the photon, the trip is instant. You left the sun, you're at the Earth, no gap. Let's go even more poetic. We have told you that when you stare out at the night sky, you're seeing starlight from stars that are thousands of light years away, or hundreds of thousands of light years away, or millions of light years away. And it is true that relative to us, the light left those stars thousands or hundreds of thousands or millions of years ago. But as far as the photon is concerned, the trip was instant. It did not experience time at all. Time on a beam of light does not exist. That's pretty cool. Oh, that also means if you've ever seen a sci-fi movie, Star Wars does this, where they're traveling faster than light, and then they're having a conversation in the spaceship. No, there's no time. And I don't mean there's not enough time. I mean time does not exist. You couldn't have a conversation. Remember I said to you, Einstein started asking himself, in high school, what would I see if I was riding a beam of light? So this was part of his answer. Well, the first thing apparently is, well, I'm not even sure nothing is the right answer, because nothing implies there's a blank, I don't even think there's that. I think the very question itself can't be asked because no time exists in the first place. Hold that thought. Next lesson or the lesson after. And part of it is I can't answer that question because you haven't yet phrased it in the correct way that it has to be phrased in order to even come up with an answer to that question. Example 7. A spaceship is traveling at 2.85 times 10 to the 8th meters per second. It leaves the Earth and returns to the Earth 100 years later relative to the Earth. So 100 years go by on the Earth. How much time has passed for those living on the spaceship? What does this question want me to find? Okay. I guess that means they told me T. What's V? This time they didn't give it to me as a percentage. They gave it to me in meters per second. They didn't give me it in such a way that I can go, do you see, do you see, do you see? So V, unfortunately, is going to be 2.85 times 10 to the 8th. And unfortunately, since I didn't stick a C next to it, because it's not a percentage, I'm actually going to have to type in the number for C, which is going to end up being 3 times 10 to the 8th. I won't ask you this very often, but on your test at least once, I will ask you for a speed in meters per second instead of as a percentage. Just, again, Darcy, because I'd like you to have an idea of how big the numbers actually are, or how small the numbers actually are. I want T0 by itself. What's the equation that has T0 by itself? T squared, right? The square root moves over, right? Times 1 minus V over C all squared. So it's going to be 100 square root 1 minus 2.85 times 10 to the 8th all over 3 times 10 to the 8th squared. Unfortunately, I don't have the C's canceling. How would I type this in? By the way, those of you that are trying to type this on your own, if you get an answer of 31.2, you did it right. But I would do it this way. I would start inside the bracket, and I would actually type 2.85 scientific notation button 8 divided by 3 scientific notation button 8. This is by far the most common mistake because kids have forgotten how their scientific notation button works. If you type it in right, you should get inside the bracket a 0.95. 95% of the speed of light, a 0.95. Is that okay? Move out of the bracket. What's the thing that's just outside the bracket? Squared. Boom, answer button squared. I get that. Move a little further out. What's inside the square root? 1 minus answer button. I get that. Now I want the square root of that times 100. And I get, 31.2. Years. So if you have you have a Casio, what's the number? Model number, top right corner? FX991. That's got a nice little 2-level fraction button, which actually works pretty well. If I could find an emulator for that, I might move to that, but I haven't found one yet. Everybody get that okay? If you didn't, call me later, because a lot of this is helping you with your calculator. Last one. What is example 8 asking me to find? V. How fast? In fact, how much time do we want to elapse on Earth? 20 years. How much time do we want to elapse on the spaceship? Really, I'm saying, how fast would I need to go to have a 2-to-1 time dilation? For 2 years on Earth, 1 year with me. How fast would I need to go if I wanted a 3-to-1 or a 4-to-1? If you're wondering how I make some of these up, I reverse engineer them using this. What do we want to get by itself? Did they tell me t? Did they tell me t0? 10? Right? Time on the spaceship, 10 years. Time back on Earth, 20 years. You could also go, is that okay, Haley? Yeah? And that, by the way, most common mistake. Well, t equals t0 all over the square root of 1 minus v over c squared. This is going to be, by far, the most heavy-duty formula manipulation we do all year. In fact, it's ugly enough, Michael, I'm going to do it once with you, and then when we get to the end, this is going to be one time when I'm going to say, let's write this equation on our green sheet, because I just don't feel like doing it again. I can do it in my head, but I really have to concentrate to track everything, and I wouldn't guarantee that I always did it successfully in my head. If you feel like it, you don't have to write the equation we're about to generate down. If you want to nerd out and derive it, you can. Here we go. Where is the v? Well, first of all, it's inside a little bracket with a squared. Inside a square root, on the bottom of a fraction. Ugh. Ugh. Well, I'll start on the outside and work my way in. The first thing I don't like is that it's on the bottom of a fraction. I'm going to times it to the other side, and now the square root is no longer on the bottom. I'm going to do this one. T times the square root of 1 minus v over c all squared equals t0. What am I trying to get by itself? What's the t on the outside doing to the square root? How can I move it over? So I'm going to do that right now, too. Look, 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 look. What's the next thing that I run into? What's sitting on the outside, on the right-hand side? What's that big mathematical symbol? Square root. So you ready? How would I get rid of a square root? Square everything. Yeah. I'm going to go like this. I'm going to square that, I'm going to square this, and really the squared and the square root will just cancel. I'll get 1 minus v over c squared equals t0 squared over t squared. Looks a little better. What's right in front of the bracket sitting right there? I hate minuses in front of what I'm trying to find. So instead of minusing the v over c squared on this side, what's that the same as on this side? Plussing. So I'm going to do two steps at once. You ready? You ready? I'm going to plus this to that side. I'll show that by drawing a little curly arrow pointing there. I'm also at the same time going to minus the t0 squared over t squared back to this side. Lyndon, I'm going to get this. A 1 takeaway t0 squared over t squared. That equals v over c all squared. I'm going to put the squared onto there and onto there. 1 minus t0 squared over t squared equals v over c squared squared. What's the c squared doing to the v squared? Dividing. How could I move it over? Times. Now, to do that, I'm going to have to put this in brackets and tuck the times right there, because it's times that whole thing. That gives me a v squared. A v what? of v squared? Anyone? Square root. So I'm going to go like this. Look up, look up, look up. I'm going to square root the c squared. I'm going to square root the bracket. I'm going to square root the v squared. Now the right-hand side works out nice. V. What's the square root of c squared? Just plain old c. And I'm going to put the rest of it inside a big square root symbol, because it's the square root of that whole thing. The last thing I'm going to do now, Reese, is instead of having the equals v on this side, just so I can show you what I want you to put on your formula sheet, I'm going to put the v equals over here. You can transfer that to your formula sheet if you wish. On the back page where all the relativity stuff, if you want to know how fast your spaceship needs to go, it's v equals c, big square root, and inside the square root, 1 minus t0 squared over t squared. We haven't even found the answer yet, but we've derived the equation. Now let's actually figure this out. How fast will I need to go? Okay. V is going to be, don't put the c in yet, just leave it. Later on I can stick a 3 times 10 to the 8th if I need to. Square root of 1 minus 10 squared over 20 squared. Let's do the square root thingy first. So I'm going to start inside 10 squared over 20 squared. 1 minus that. Square root of that. And if I evaluate the square root, ignoring the c, I get 0.866. Yeah? So I get this. V equals 0.866c. How would you read that as a percentage? .6% of the speed of light. If the question said give your answers as a percentage, you quit here. You don't need to put the c in. If they wanted it in meters per second, I could then go one step further. I could go 0.866 times 3 times 10 to the 8th, the actual speed of light, and I can give you the answer in meters per second if you want. This number times 3 times 10 to the 8th, 86.6% of the speed of light, or 2.6 times 10 to the 1, 2, 3, 4, 5, 6, 7. Oh, of course it's 8, because 3 times 10 to the 8th is the speed of light, so 86% would be something times 10 to the 8th, right? Meters per second. Up here you can write 86.6% of c. That's one way to answer it. Or if you want it in meters per second, that's what your speedometer would have to say relative to the Earth. Your homework now is every question. So now you can tackle number 4 and number 6. You can tackle also 14. 15 is where you're solving for V. 16 is where you're solving for V. 17 is where you're solving for V. 18 and 19. So I have attached the answers. Also, if you go to pitmath.com, if you click on block E, click on special relativity, you will see there's something there. I think it's called lesson 2 homework answers or something like that, where I actually showed everything that I typed on my calculator and showed on my steps if you get stuck.